So my background is very much in natural language processing. I developed an open source library called Spacey. And so, I'll start showing you how these things work and basically try to give you this little insight or aha moment in how these solutions are put together for natural language processing problems. So if I were to give you sort of one weird trick to understanding machine learning in general, I would say that it's to take a computer's eye view of things. So definitely don't anthropomorphize. Like think of the algorithm itself and try to step through it without thinking in sort of magical terms about the knowledge that you have that can't possibly be inferred by the algorithm that's coming. And so as an example of this kind of process of taking a computer's eye view of things, imagine that you don't speak Indonesian. I've tried to choose an example that's not much of a stretch for most of the audience. So imagine you don't speak Indonesian and you're given the task of understanding from 10,000 restaurant reviews whether a review is positive or negative. So you've got this pile of reviews, you're given a quiet room, pencil and paper, a week and a lot of coffee. So what sort of process could you come up with from this to make new predictions? Like at the end of the week, you're going to get new reviews that you haven't seen before, and you need to tell whether they're positive or negative. So based on this 1 week of sort of training that you have to come up with a system. You have to come up with a coding solution for this. So what could we do about this? So let's see what this sort of problem looks like. So here's some examples of Indonesian restaurant reviews. Now, what we absolutely must not do is cheat in our understanding of this. Oh, no, okay, I'll not use that button. Okay, so you see down the bottom here, there's this thing, cozy place, and there's another one which says avocado and things. And, you have knowledge that you're importing from this, that, okay, this looks pretty good. Like, this one looks like it's positive. That's not going to help you. That's not going to help you solve this problem of coming up with a system for this. You have to imagine that you're at a computer and you don't, cozy is as foreign to you as enact before it, right? So we need to come up with a way of figuring out whether the review is positive or negative just based on associating the text to the labels. Now, when we're doing this, the key is to come up with some sort of reductionist solution. So some sort of figuring out of what doesn't matter, some sort of way of generalizing. And by this I mean that we have to figure out some solution that throws away information. If we tried to process each text holistically as the whole text, then every text is basically unique, and so we're not getting any further. We have to figure out what the lower level features that are common between them, and base our solution on that. So it has to be unsatisfyingly dumb in some way, because you can't assume that you're going to understand the whole text, because you don't. You've only got these 10,000 reviews in this one label, right? That's not enough to learn Indonesian. It's like impossible. So the solution can't be read the text, decide what it means, decide whether that meaning is positive or negative, code it as positive or negative. It has to be simpler. And it's going to be the same for our machine learning solution, right? So there has to be something that we're throwing away. And so the question is, what should we do here? Well, here's a solution that would be pretty good, like a way that you could do this. All right, take a review. The first review, one by one. Start counting out the words. For each word, track a positive or negativity score for that word. Start off with the scores being all 0.5. So in our first review, all of the scores are 0.5, so we're going to come up with a score that's 0.5. Now look at the label. If the label's positive, then take all of the scores that you had for the words in that review, and if it's positive, we have to say, we undershot. So we should increase all of these scores. All of these reviews, all of the words in this review should be more positive than my current theory. If, on the other hand, our score was greater than 0.5, but the review is negative, we say, okay, I overshot. All of my scores for these words have to be slightly lower. So let's lower them all. And then if we have a score that's greater than 0.5 and the review is positive, we'll say, okay, my theory was all right, next review. So you can see how if you stepped through this process, you would be writing down on this piece of paper a score for each word, and you're just tracking those scores. And so if you keep iterating over this process, you're going to end up with a solution that allows you to sum up from just the words in the review whether the review is positive or negative. And from implementing this a number of times in code, this as a solution to this actually isn't bad. This way of solving this problem, and so you can see here. All right, this is the sort of dumb solution that that you can take that doesn't assume any knowledge or sort of human level understanding that can actually drive us forward and get us a solution to these problems. So that's kind of what it means to implement a solution that understands language in this way algorithmically. It doesn't really understand language, but it can come to a prediction based on this data and even very limited data. So what are the ways in which the solution that we've come to are unsatisfying? What sort of errors will we get compared to a true understanding? Well, we're assuming that different words are unrelated. And that means that if there's some word that we haven't seen before, even if there's a really similar word that we have seen before, we're going to not be able to leverage that similarity. We're not going to get any. Every word is an island in our understanding. So in Patrick's terms, it's we've got this one hot encoding. We're treating every word as a different vector, when we would do better if we could understand more of those similarities. Then we're also assuming that words only have one meaning. So we're assuming that when we see a word, that word, regardless of its context, is associated to exactly one vector. And we also know that this is wrong. Words change meaning based on their context. And then finally, we're also assuming that the meaning of the text is kind of this sum of the parts. We're making an independence assumption about these words, and that's also not true. So based on a sentence overall, that sentence has a meaning or that text has a meaning. But we're throwing it away. Again, that sort of throwing away process is the thing itself. It's those generalizations that allow these things to work. But what we'd like to do is, instead of bringing for every one of these problems, bringing in those generalizations to start with, instead of having to come up with these algorithms, come up with intelligent solutions for what to throw away, we'd like to be able to learn that. We'd like to be able to learn these reductions intelligently. So we want to know, if the right thing to do for this problem is to treat every word independently, cool, we should come up with that solution. If, on the other hand, the right thing to do is to pay attention to a narrow context window around each word, we would like to learn that. So how do we do that? Well, now with neural networks, we've got a good way of automatically building these representations. And the sort of framework that I think is useful to think about this and to understand that complexity and to break it down a bit is to think of it in terms of these 4 steps. And the 4 steps are embed, encode, attend, and predict, where embed is the solution that we saw in detail in the last talk, and there's these 3 other processes that I'll talk about in very high-level terms as well. Okay, so in order to sort of get a perspective on this or a handle of this, because, as I said, it's quite an abstract approach to this, it's important to remember that we're thinking about sort of problem shapes rather than application details. So we're thinking about the general problem of transforming one representation into another. And so we've really only got 4 species of representation here to manipulate, and that's why we have such a limited vocabulary of steps, because there's only so many operations to make. So here we have the ID, which is an integer category label or a word label. So it's one in a discrete inventory of things. A vector for a single meaning representation. A sequence of vectors, which is say we've got each word mapped to a different vector, and then we just put them in a sequence. And then finally a matrix where we've kind of tangled the meanings together and we're taking into account the context of the words more. And so the transformations between these are, these kind of fundamental shapes mean why we have only these 4 operations, which I'll explain. So, and this also goes to solve those 4 problems which I mentioned before. So the first problem which Patrick's talk went through in detail is that all the words look unique to the computer. So if we have dog and puppy and we map those to IDs, well, those IDs are different and we're not gaining any of this generality. So if we've got a solution that knows that dog means something positive, then when we see puppy, we can't leverage that existing knowledge. And we'd really like to take that into account and to not treat every word as unrelated, because they're not. So this is this embedding process that Patrick said. Instead of having the words be one-hot vectors or completely unrelated. We want them to be these dense representations so that we can see whether a word is similar or dissimilar to another word in various respects. And that there's various algorithms for calculating this, like the word-to-vec algorithm, which Patrick said, but also point-wise mutual information, latent semantic indexing, etc., etc. And these all get to this fundamental insight that we can know a word by the company it keeps. We can look at the words that surround the word in general and use that as a proxy of what it means. Okay, so then the next problem that we might have, or the next way in which our solutions can be unsatisfying, we're discarding context if we just take each word independently. So if we have these two reviews and we look at only the words between them, we really have no hope of saying that the first one's positive and the second one's negative. Like if you, again, take the machine's eye view and don't think of this in terms of reading the whole sentence, imagine looking at these as just isolated words. In which word of this tells you that the first one's positive? Like maybe people use literally more when they're being sarcastic, and so they, you can say, all right, maybe we've got some hope of saying that the second one's kind of weakly negative. But if you treat these words independently, you're not gaining anything. It's kind of like, imagine trying to learn who won a game of tic-tac-toe by looking at all of the piece movements individually. You need to look at a larger configuration to figure that out, or trying to figure out who won a chess game based on just seeing each of the squares all jumbled up. You need to look at a larger configuration to see that information. And it's the same with some of these sentences. So in this case, you need to look at the larger scope of the meanings to see that the second review is negative and the first review is positive. So how can we do that? Well, that's this encode step. And so in particular, the bidirectional long short-term memory unit has been particularly revolutionary in natural language processing for this, but also convolutional layers and other ways of doing this. The fundamental insight that we have here is that we're going to take these dictionary meanings. So the step on the left is a sentence represented as just each word from a dictionary. And then based on the surrounding words, we're going to re-encode them. So we're going to say, all right, if I start off with this sort of generic dictionary meaning of duck, and I look at the words around it, how can I refine the meaning representation that I get out? And that's what this step has been all about, and this has been very helpful and reduced error rates for a large number of natural language processing tasks by 10 to 50% sometimes, depending on exactly the task that you're doing. If we were just trying to classify our reviews, probably this usually doesn't help so much, because individual words like good and bad are really pretty useful for processing individual reviews. But for other tasks like translation or figuring out whether some sentence means the same thing as another sentence, it's super important to look at these larger scopes around the words and get these more individual senses. Okay, so then another problem that we might have of this, if we're back at the previous state and we've got this sort of matrix representation of our sentence. Well, the next problem is that we kind of have too much information. We don't want to have a meaning representation for all of the words of the sentence. We want to get forward and we want to start discarding more information. If we don't just want to say, well, this is the meaning of all the words in the sentence. We want to say, what's the meaning of the sentence overall? And then finally, what's the thing that we're actually trying to predict? So we want to go from that sentence representation that we have here, this matrix, to a vector. So what's an intelligent way to do that? Well, an unintelligent way to do that is to just sum all of the rows at a vector. And actually this works pretty well for a lot of situations. We can also just take the element-wise maximum of the vectors, and that also works pretty well. But we'd hope to have smarter ways of doing this. So here's, this is where this attention idea that's been very popular in natural language processing and other neural network fields has come in. And so what we're doing here is taking some sort of query vector or even a query matrix, and then this allows us to compute some sort of weighted sum over our sentence representation. So in other words, this sort of fairly simple operation of figuring out what matters and what doesn't in a fairly easy to learn way can help a lot for a lot of tasks. So for instance, if you're doing translation, the input query might be the sentence that you're translating, and the other side of the candidate sentence, and now you're going to sort of reweight the representations that you have based on that. So yeah, this also is a very helpful and general way of solving these natural language processing problems. Okay. So, and then finally, the last step of this that in this sort of 4-step framework, embed, encode, attend, predict, is actually getting the predictions. So, you know, after we've done all this work of coming up with a representation for the sentence and learning that representation, we then want to actually get an output value. So we want to actually predict to an ID. So, you know, because the point of all of this is that to actually sort of plug it into a larger application. The idea isn't to just compute representations of things. We want to actually get the value. We want to do the thing that we are trying to, you know, make use of the network. So here, for instance, we might want to get the actual review score of the, you know, of the review that we're trying to classify, or we might try, want to know whether these two sentences mean the same thing, or anything else that we're trying to train the network to do. So, and this is, fortunately, this is, you know, basically back at the very well understood problem of, you know, manipulating vector representations and things. So this is just a sort of feed-forward network. So here we want to turn this generic representation into the specific solution and provide, you know, the actual value to the application. All right, so now I'll outline 2 networks that actually in total are pretty sophisticated and pretty complicated over the last 2 years that have solved different problems that can be understood in terms of these fairly simple building blocks. So how easy is it to see the details of this? I mean, it's pretty broad shapes, but you know, I know that the room goes back a bit, but I hope that it can be seen. This is a diagram, sort of diagrammatic representation of a paper from 2016 from some researchers at CMU that they titled A Hierarchical Neural Network Model for Classifying Text. So this can be used for any type of assigning ID scores or sorting text into different buckets. And the texts might be long or short, but in particular, this is, has been used in, it has a special advantage for texts which are fairly short, like a couple of sentences or more, which otherwise, if you only look at the word IDs within them, is a quite difficult problem. So at the top layer here, we've got this embed step. So imagine that we've got, and you can kind of read this as having a sentence, one sentence on the left and one sentence on the right. So we're feeding in 2 sentences here, and we take these IDs for the individual words in the sentence, and we separately embed them all into the table so that we get word vectors for them using the, where the word vector table might be learned with a process like Patrick showed you. And then after we've got this representation, which you can sort of think of as a bunch of dictionary definitions after each other, we then want to encode, we then do this encode step, which might be a bidirectional LSTM or a convolutional neural network or some sort of module like this. And based on that, we're going to get 2 representations of the sentences. So in other words, 2 representations of all of the words in context. And this is able to take into account different word senses and things so that, you know, imagine that you've got a word like duck, which can be a noun or a verb. Well, we start off with a meaning representation that has to represent all of those senses, and then based on the surrounding context, we can get a vector representation that takes that word into context. So now we've got these 2 sentence matrices next to each other. Next, we can use an attention layer to produce a weighted sum of these, of all of the words in the sentence, so that we get a single vector for each of these 2 sentences. So now we have a sequence of sentences, where before 2 steps ago we had a sequence of word vectors. So now, once again, we take an encode step. So we look at these sentences in context. And this is able to take into account these sort of ordering effects and transitions of meaning from one sentence to another. So that even if there's the thing that makes the review positive or negative resides in meaning relationships that are beyond the single sentence, the model is still in principle able to learn that. And then, so out of that, we get this encode step of a matrix for all of the sentences in the review. And then we repeat the attention layer and we say, all right, now we've got this sort of more complicated representation. Let's get a representation for the text as a whole. And then finally, based on that text as a whole, we can make a prediction of positive or negative for the review. Now, again, a thing to understand here is that it's kind of nice that we've got, in principle, any of the information could flow through this. So in principle, the model would be able to learn things about reviews that make them positive or negative that reside in larger than sentence units. Now, it might be that that almost never happens, and it might be that the review model that we actually learn almost never pays attention to these ordering effects that are larger than a sentence. But that's fine. It's not a failure of the model that, it's not a failure of the algorithm if we get back a model that doesn't pay attention to those things. What's really nice here is that it might have learnt that. We don't have to assume that going in. If the data was such that it needed to take advantage of those things, then maybe it could learn that. So even if at the end of it, all it's learned to pay attention to are individual words, we still gain something from taking this sort of approach because we don't have to build those assumptions into the layer. And that means that we can really generalize these solutions much more. So, we can build a model that says, all right, in general, this is able to learn labels of text. And it might be that we train this on one type of problem where it only needs to pay attention to words out of context and learns a fairly simple representation. Then we use this on a different sort of problem, and actually it's sort of much more intricate, and it learns a much more intricate solution. So that's really nice. We don't have to do problem-specific engineering. We can come up with an algorithm once that does this. And so this is quite satisfying. So here, this looks fairly similar, but actually the problem that we're applying this to is quite different. So instead of taking one text as input, here we're going to take two texts as input and predict whether some relationship holds between them. So for instance, we might predict whether this sentence is an answer to this question, or we might predict whether this sentence implies another sentence, or we might predict whether this sentence implies the opposite of some sentence. So in order to do this, we can once again embed our IDs into this type of representation where we just have a sequence of vectors. Then we do the encode step and take those vectors into context. And then we're going to perform this attend step where based on the two sentences as input, so we've got the two matrices, we're going to use an attention layer to come up with a weighted sum for a single vector. And that single vector is going to represent the combined semantics of those sentences, or the relationship between them. So you can see here that the sort of building blocks and representations that we're manipulating are still very similar, even though the task context is very different. And so we can stitch together a solution that for this quite different problem using the same building blocks and come up with something that can solve this quite different problem. So again, we're gaining that generality of knowledge and having to do much less manipulation that's specific to these things. So this comes from a paper from some researchers at Google in 2016. Okay, so then sort of wrapping this up, what do we do if we don't have 10,000 reviews? Like, what do we do if we have much less data? Well, the general solution is that we want to import as much knowledge as possible from outside of text. And so this is where coming up with these unsupervised methods of learning representations is very useful. We can come up with these word embeddings that Patrick mentioned. More recently, people have focused a lot on coming up with representations of words in context. Some work up in Seattle at the LNI Institute has been very successful at this. And finally, transferring knowledge from one problem to another. And so what we really want to do is learn from smaller and smaller data sets so that we can tune them to very specific problems. And we want those data sets to be focused very much on the business problem that we're dealing with. So we want to learn what to pay attention to and what to predict. These lower level things about what the language means in general, we want to learn from language in general. And this makes a very satisfying deal of sense, right? Like, if you give somebody a task, you don't want them to relearn language in order to solve the task. That you want them to import that into the thing to start with. So in summary, these neural network models, even if they come up with a solution that's quite similar to what you would learn from a simpler algorithm, there's still a real benefit in doing this because you don't have to assume so much going in and you don't have to do a fair bit of less fiddling around. Instead, you often have to do different fiddling around, which is not so satisfying at the moment, but we're steadily making progress at that. And especially as more compute power comes available, we learn more about how to make that process more automated. Another thing to keep in mind is that the knowledge has to come from somewhere, but ideally the more knowledge that we can import from unlabeled text and unlabeled generic representations of language, the better. But in order to actually apply that to a text, apply that to your business problem as acutely as possible, you do want to tell it exactly what you care about. And that's why we do often want these labels that say exactly the thing that you want to do. You want to encode your problem into these labels. And that's what we'll hear more about in the next talk. And then finally, the general shapes are now well understood. So these general shapes of data and general types of transformation. But there's lots of different solutions for these, for each of those problems, and there's lots of refinements going on and coming up with better ways of encoding vectors in sequence, or more efficient ways of doing these things. So there's lots of innovation going on in that respect as well. Okay, thanks.